Thank you everyone for coming back online for day 2 of the Computational Physics School for Fusion Research. My name is Greg Wallace. I'll be the chair this morning. I'm a research scientist at the Plasma Science and Fusion Center at MIT. And this morning we will have, I guess morning depends on where you are, but let's say the first lecture today will be Dr. Tim Mattson from the Intel Corporation. Tim is a chemist by training, but has been working for many years now at Intel, where he worked on the first teraflop computer, different research processors, and is now the senior principal engineer in Intel's Parallel Computing Lab. So with that, I'll let Tim take it away. I mentioned one brief thing before you start, Tim. Earlier I mentioned to everyone, but I'll say it again, if you have questions, please try to use the Discord chat channel, OpenMP-MPI-GPUs. The record of that will continue after the lecture is over, so we can continue to have interactive questions and answers even after the Zoom session ends. If that's not working for you for whatever reason, you can use the chat function in Zoom. Jessica and I will be monitoring that if questions or issues do come up, but that interaction will freeze and the chat session will not be available to everyone after the end of the lecture. So that's why we ask you to please, if you can, use the Discord chat instead. So with that, Tim, please take it away.
Okay, so let me share my screen.
And Tim, I think I saw John Wright join just now.
Oh, good.
So, okay.
Yes, I'm here. Everyone can see my screen now.
Yes, we can see it just fine, Tim. Thank you.
The most challenging part of the day is behind us. There we go. Okay, so we're about to start an exciting journey. We're going to learn about parallel programming. Wait a minute, I want to turn my video off because you really don't need to see me. Stop video. There you go. Okay, this is cool. So today we're going to do an introduction to parallel programming. And I'm assuming that it's an introduction, that you folks aren't parallel computing experts. And therefore, we're going to go through everything from the beginning. And so by the end of today, you will be officially parallel programmers. So, which is totally cool, because the coolest people in the world write parallel code. And I use OpenMP for that. And the reason is that OpenMP has the smallest learning curve before you actually get up and running writing parallel code. It takes very little time at all until you start working with writing parallel code. The hardest thing with parallel programming is the algorithms. It's understanding how to think about things in parallel. It's to think about how you manage concurrency running on multiple resources. That's the hard stuff. Whether you spell it with OpenMP or CUDA or MPI, that's secondary. So we're going to learn about parallel programming, and we're going to do it through OpenMP. Everything and more, a huge amount of material is available on GitHub, and there's that site at the bottom of this slide. So what I would do at some point is go on your laptop and clone that GitHub repository, and you will have everything, slides, exercises, the works. So, okay. Can I advance a slide? There we go. So just as way of introduction, what I really am, and that picture is taken just maybe a mile from where I'm sitting. I'm just a simple kayak instructor. That's what I am. But to support my kayaking habit, I work as a parallel programmer. And what does it mean to be a parallel programmer? A parallel programmer is someone who knows how to turn math into lines on a speed up plot. So that's just as simple as can be. That's what parallel programmers are. Oh yeah, I work at a big old international corporation, And we have to always put this in. So it basically means no matter what I say, don't sue Intel. And I'm not going to say anything about a product. And if I do, I didn't mean it. The real part is these are my views. A lawyer did not go over these and approve of everything I'm saying. And I'm not speaking for the OpenMP Architecture Review Board, the organization that owns the spec for OpenMP. Nope, just speaking for myself. I have a request to make. If you could just sort of like, keep off to the side a piece of paper or something and just jot down places where you think the tutorial could be better. I'm always open for constructive or even not constructive feedback on what could be done better. So here's the plan for the day. This may be quite different than other tutorials you've taken. As a person trained in athletic education, kayak coaching, the thing you learn in coaching physical activities is that no one learns by listening. Or they don't learn well. People learn by doing. And so therefore, what I did in designing this tutorial is I took what I learned from kayak coaching and I applied it to parallel programming. So I try as much as possible, the learning happens through exercises. And the whole idea that I talk at you all day, then give you a bunch of exercises, that doesn't work. What works is I talk at you for 15 to 30 minutes, then give you an exercise. Some of the exercises will take 5 or 10 minutes. Some of them will take 30 minutes. But my goal is that you spend, I mean, in my dreams, you'll spend half of this time, our time together, actually doing exercises, not just sitting and listening to me. I love to listen to myself speak, but I don't see why any of the rest of you would. So short lectures with short exercises. Now, your laptop works just fine because laptops support lots of threads with any modern operating system. And pretty much any laptop you would buy today has multiple cores. So you can do everything on your laptop. Or you can log into the system that they've provided and work there. So either works just fine. I have simple rules you have to follow. When I give you an exercise, do the exercise as I tell you to do it. I have very specific reasons for every exercise I give you. So if you have a little bit of advanced knowledge or even a lot of advanced knowledge with OpenMP, don't cheat. So you need to go in and just do the exercise as I do. Don't cheat. Don't look at the solutions. I've given them all to you, both in the slides and online in the directories with the exercises. Don't look at the solutions before you complete an exercise. Now, if you have some OpenMP background or you get done really fast, don't stop. There's no reason to ever be, bored. What happens if you ask for 1,000 threads? How does the performance change as you increase the number of threads? What if you decompose the algorithm in different ways? There's tons of things to dink around with these exercises. So if you're someone who moves really fast, don't get bored, experiment and learn. All right, so I'm watching the Discord chat, so I will see questions in real time as they come up. And we're gonna go ahead and get started. Sound cool? All right, sounds cool. So OpenMP. So OpenMP is an API for running multi-threaded applications. That's what it was when we created it. It's actually done a little bit more now because now we've added heterogeneous device programming, GPUs. But at any rate, it's a set of compiler directives and library routines for you to write parallel applications. And our goal was to try and make it as easy as we could for you to write multi-threaded applications in Fortran, C, and C++. And later we added explicit vectorization and we added GPU programming, but the core roots of OpenMP is all about multi-threaded programming. And that's what we're gonna focus on today. So let's talk just briefly about OpenMP. I, by the way, was involved from the very, very beginning, prior to 1.0. So I've been involved from the beginning. And so it started, the spec was 40 pages. I could teach the entire spec in less than a day. It was simple and easy. But as you can see, with each new version, it's gotten bigger and bigger and bigger. The latest formal release was, and this is actual spec, not the front material or appendices, the actual definition of the API and directives was almost 500 pages. So what started as this simple little spec for getting you all going has become a monster for experts only, unfortunately. It's become very complicated. But fortunately, it turns out that if you look at that whole massive, thick book of a spec, most people only use about 21 items from the spec. I call these the OpenMP Common Core. Everyone working with OpenMP uses these, and most people working with OpenMP, this is all they use. So the strategy I take right now, which by the way, I learned from Bill Gropp and folks in the MPI community, is, it's almost like I have my own spec, and it's the Common Core, and it's these simple constructs, just 21 of them. And as I said, you download most hardcore official production-worthy applications, and it's rare that you will see them using more than one of these 21 items. So by the end of our time together today, you will have mastered all of these items on this list, and you will be ready to do professional grade OpenMP programming. So it's pretty cool, pretty awesome. All right, so let's get some basic definitions out of the way. So, what I call the full stack solution for OpenMP look like? And of course, at the bottom, you got hardware. And the current spec, that hardware is, you have a shared address space, and it has non-uniform features, meaning it's not just a flat address space. The cost of getting from any location in memory to any thread can be different. That's what it means to say NUMA. And we have these offload directives that let you move from the CPU onto a GPU, so a complex hardware space. Then you have the system layer. And this OpenMP assumes you got an operating system, you got the Open Fabric or some other way of getting over the PCI or whatever connection to the GPU. That's all built in, and OpenMP assumes that it's there and given to you. And then you have the OpenMP runtime, which is the first place where in this stack where OpenMP has written something specific. This is the low-level libraries that you, or even me, I never touch. Now, the programming layer, the blue, this is what we're talking about today. What are the directives? Most of the action happens with compiler directives, okay? There's a runtime library, which is things you call that you can only, if you need information that's only available at runtime, you can't do it with a directive. So that's the runtime, the OpenMP library. And then there's some environment variables, so you can set up things for the running program. And then there's the application and the user layer. So this is the basic stack of OpenMP. Now, for us today, we're even going to simplify it further, because today we're just going to look at assume a shared address space that's a symmetric multiprocessor. The word SMP gets thrown around a lot, and it's often used incorrectly. So symmetric multiprocessor means every processor is equal to the OS. The OS doesn't play favorites. It also means that the cost function from any location in memory to any thread is the same. And of course, those aren't true, but it's actually a very effective approximation. And it's uniformly made in multi-threaded programming. Now, one of the things I've learned is when I do this tutorial and I find a typo, if I don't fix it on the spot, it never gets fixed. So there we go. All right. Okay, so that's the plan for today. All right. So the basic syntax. I've been talking at you too long, but this is just stuff I have to get out of the way. We're going to teach the course in C. I assume you all have a knowledge of C. If you don't, in the directory of exercises I gave you, so see here we have something called exercises, and in OpenMP, if I go down, see this file here, learning.c.c. Okay. What I basically did is it's a C program, but I go through in this program and I review all of the elements of C we use. I suspect it wouldn't take someone 10, 15 minutes if you were a Fortran programmer. It might be harder if your only experience of programming is Python, but definitely for the Fortran programmer, it would take you 10, 15 minutes to go through this and know all the elements of C that we're using. So I have found it's not a problem that we do this in C. But I like to point out, OpenMP is defined so that what you learn in C seamlessly moves directly into Fortran. And I'm not going to go into it at all in this tutorial, but I'm darn excited. If you contact me offline, I can talk to you about it more. I have defined a Python binding of OpenMP. It is so cool. And I happen to work with someone on my team who's someone who's used to mucking around in the guts of Python. So the two of us working together, we have a working prototype of a Python binding to OpenMP. So in the future, I'd have the option to teach this course in Python. Totally awesome. But the Fortran specification defines it for C and C++ and for Fortran. And so a pragma is you tell the compiler to do something. That's what a compiler directive is. So this is tied to the compiler. And so in C and C++, they have pragmas. And so the pragma is always, the hash pragma, OMP, and then the name of the construct and a set of optional clauses. In Fortran, we do this by a decorated directive. So I use the exclamation point, but any of the Fortran comment tokens can be used there. So, exclamation point, $OMP, the same construct name. So this is why I say, if you know it in C, you know it in Fortran, then the set of clauses. All right, so pragma OMP parallel private is an example where the construct name is parallel and a clause private. We'll explain that later, don't worry. And gosh, I should have had private on my Fortran. There's another error, but I won't fix it now. The only difference between the C and the Fortran is C is a fundamentally block structured language. A block is either one line or multiple lines between curly braces. So we didn't have to do anything to define a block of code we're going to pass to OpenMP. Fortran is not block structured. So we have to add in Fortran, but not in C, a closing directive. And it's always the same. The Sentinel $OMP end construct name. Simple as that. And then in the C program at the top, we always have, pound include omp.h, or in Fortran, we use OMP live. Simple. So these constructs apply. So you have the directive and its block of code is called a construct. And this construct is the code in between those curly braces. It's one line or the code between the curly braces. And the rule is that you can only enter that block of code at the top, and you can only exit that block of code at the bottom. The only exception is an exit or a stop statement. Now, this is needed because remember what the directive is doing is it's telling the compiler, hey, compiler, take all this code on this block, turn it into a function, and then pass this function to an operating system thread. So the compiler has to be able to turn all of these statements into functions that it can pass to a thread. That's called outlining if you have compiler friends you talk to. So, so at any rate, that's what we've got there. We call that a structured block. Okay, so exercise A. This is where we go off and we make sure that we can access a compiler and a text editor and can get on whatever system we're going to use. This is when we pause for you to do that. So what I want you to do is, using the editor of your choice in your environment, write this code. It's a hello world program, and do it hello and world on separate lines. Go for it. This hopefully is a very fast exercise, but it sometimes can take a while because this is where if people are having problems getting onto the system, if people have problems getting on the system, this is when we resolve them. So off you go, have fun. And by the way, the communication going through on the on our chat channels. Should be very noisy. You know, when you're done, let me know. If you're having any issues, let me know. If you need help, let me know. You know, we should have a lot of dialogue going on right now. All right, go.
So Tim, we have one user who's trying to get their password reset. But
Okay,
right, don't see any other issues.
well, that's good. Yeah, I had no problem with OpenMP on your GPU cluster. I never could get OpenMPI to work. I could get it to work on one node, but John and I could never get it to work multi-node. So that might be okay. We're not likely to need MPI, so I don't think it's going to be, but I can make it so it's not a problem. Let me put it that way. I can make it so it's not an issue at all. But
Right.
it still bugs me because I do lots of MPI programming and I've never had this problem. So there's some weird setting that's getting in the way.
Yeah, so I mean, the issue with OpenMPI on multiple nodes on sort of this bare cluster is that that I didn't like for each. Generally, when you create a user, you set up some sort of passphrase free SSH key so that OpenMPI can launch SSH processes seamlessly.
Yeah,
We I don't have that script in place so that when we add a user, it's not done automatically. And that's really the source of the problem. I should
but
probably
I did that by hand last night and it still isn't working.
no. Okay, well,
Yeah, so there is another issue because I did that.
okay, well,
Um,
if you can send me if you have an error message, you could
there are
send
no
it.
error messages, it hangs.
It
Isn't
just
that,
hangs.
isn't that
Okay, well,
frustrating?
that is frustrating. That sort of points to a login issue. I'll poke around and look at that for you. I'm sorry for the trouble, but I mean, there are 40 cores on each node, so there
Yes.
should be some level of scalability that can be studied. You just kind of miss the, node one talking to node two kind of thing.
See, that's my feeling as well. That's
All
right.
right.
It's
All right,
just
I'll
not an
poke
issue.
around on that and let you know if I can fix it quickly.
Yep.
Thanks. And yeah, if anybody's still having issues, either email me or put something in the chat.
That sounds good. So is anyone having problems? Now would be the time on one of our communication channels to let us know. Are anyone having problems?
It looks like we're having a couple people that are still trying to get login, but I see a few reports that several students have gotten the hello world to come through successfully, little screenshots showing their proof.
Awesome. Okay, so I'm going to go through to the next exercise. I'm assuming you're all okay. And remember, you can do this on your own laptop. You can do this on the system they provided, the GPU cluster. So that's awesome. So now here comes, oops, get back on the right screen. Okay, here comes the next exercise. So now what I want to verify is that your OpenMP environment works. All right, so here's what you're going to do. You're going to put a #include omp.h at the top of your file. And by the way, we'll go back and explain all of these later. So don't worry that I'm just telling you to type these in and do something. We'll explain it later. So then put a #pragma omp parallel open bracket and then a close bracket after your hello world. Do that. And then you're going to compile it. And I'm assuming you're all using the GCC compilers. Some of you might be using an Intel compiler if you want, but let's just assume everyone's using a GCC. So GCC, and then the line to tell it to look for OpenMP and link in all the OpenMP libraries, GCC-F OpenMP, and then your program. Okay, so that's GCC space -F OpenMP space your hello world code. So do that and then run that and see what happens. And this is where we find out, remember, the big purpose of this exercise is, do you indeed have a compiler that knows OpenMP? And if you're really running with a GCC compiler, the answer to that question is yes.
So Tim, we have a question for you. Does the C syntax require indentation for a block nested within another block?
Nope. Nope.
Okay, so
Yeah.
the
Python
curly
is,
braces take care of everything, right?
curly braces take care of anything. Python is the only modern language in use today that I know of where white space is syntactically relevant.
Okay, thank you.
Yeah, I must admit, for those of us coming from what I'll call the old boring languages, one of the hardest things to get used to moving to Python is the fact that white space is syntactically relevant.
I completely agree with you on that, Tim. It trips me up all the time.
Yeah.
Yeah, well, the choice is between white space or curly brackets. So, but yeah, I agree. Especially the whole tab and space issue when cutting and pasting code.
Yeah.
Just like, oh my God.
Well, we get used to using white space to reflect readability issues. And it's like, nope, can't do that. So, all right. And this one should go fast. Now, remember, we just had on the, what's this called? The chat system we're using.
Discord.
Discord. Thank you. Because I never use it. It's like my brain. Someone showed their screen on Discord. Remember, I wanted a separate print for hello and a separate print for world. So
you would know what Discord is if you lived with a gamer.
Oh, would I? Okay.
Because it has a voice channel and they use it all the time to like coordinate, military strikes in their video games.
Oh, right, of course. Okay. Yeah, my children are adults and they grew up and moved out before Discord became available. I imagine they use it now.
So Tim, to be clear about what you just said, when you said you wanted a separate printout for hello and world, does that mean hello and world should be on two separate lines? Or
exactly as I have it on my screen? Printf hello.
Okay.
Printf world.
And with a new line after the world. Okay. And
it's not a huge deal. The person who's giving a picture of their screen there, that's fine. That's great.
And with the OpenMP version, it should print out multiple times for each parallel thread, right?
Yep. Because what we just did here is we didn't tell it anything at all about how many threads to use. We just said, hey, system, use the number of threads that you make available by default. And usually it's the operating system thinks, how many cores do I have? And keep in mind, with a modern CPU today, there are more hardware threads than physical cores. So the default number of threads is usually, but it doesn't have to be. Let me be clear. It's left up to the operating system. It's left up to the operator of the system to set these defaults. But there's some default number of cores that the operating system sees. So.
Is anyone having trouble with
Well, let me be clear, you're not
exercise?
running on a GPU right now. You were running on a CPU. Even though you're on the cluster says GPU, you were running on a CPU. And I will talk about OMP num threads later. Don't worry. All right, so I'm going to assume everyone got that, right? Is everyone done up till now? Once again, the procedure we have to use is when I say, if anyone's not done, you have to tell me, oh, I'm having trouble. Whoa.
Okay, we've got Vincent's having trouble with the compiler not finding stdio.h.
Yeah, you don't have an underscore. Drop the underscore. And I want to thank the person who answered his question, because when people ask questions, don't be shy if you know the answer. So we're going to move on.
We have another file executes, but nothing prints from Andrew Maris.
I have never seen that one before. This is where this tutorial is hard to do interactive, because normally what I'd be doing right now is walking around the room and sticking my faces in screens and helping to debug. So, all right, I'm gonna keep moving though, because we're gonna have a longer exercise soon. So, so here we go. The OMP.h is the include file. Any OpenMP program, that has to be the top. The pound pragma OMP parallel, this is called a parallel region. And what I'm going to do is I'm going to start up a number of threads, and each thread will run the code in the parallel region. And then that last curly brace closes the parallel region. And when I run this on my laptop, I get this. Hello, hello, world. New line, world, hello, hello, world, world. And if I run it again, I'll get something different. And if I run it again, I'll get something different. So what I want to emphasize here, and this concept is extremely important. When you have a collection of threads running, they are unordered with respect to each other. That's what it means to say they are concurrent. The word concurrency gets horribly misused. Computer scientists just piss me off about their abuse of language. Okay, concurrency means you have lots of things happening and they are unordered with respect to each other. That is all concurrency means. The C++ specification defines concurrency incorrectly, and they should know better. It pisses me off. Anyway, sorry. So they're unordered. What that means to you as the programmer is that every legal way that you can interleave the statements can occur. I call it the multi-threaded reading of the program. So while one thread is printing hello, another thread is printing world, and then another thread prints hello, and therefore you get two hellos and you might get a world, because now they're going through another thread inside the operating system that manages what goes out on the screen. And so you have all of these things, and they're all happening in principle at the same time. In principle, I say, because the operating system is interleaving and switching threads in and out, right? I mean, there's just like chaos going on behind the scenes. The operating system is swapping threads in and out, so you feel like, as the human user, that the latency to any given thread is instantaneous. On a human scale, you're not supposed to notice it. But when you're writing a code that's going to be running on multiple cores, you will see it. So this is the interleaving of the statements, and every interleaving is possible. And this is the challenge of multi-threaded programming, because you have to write code that no matter how those statements are interleaved, the answer is correct. And that is trivial in a case like this, where I said print hello world, and I don't care if you interleave them. I didn't say make sure it says hello world, then hello world, then hello world, right? I didn't say that. So in this case, we didn't care, just do it. But you have to make sure in writing your code that every single way that those statements are interleaved is okay. And if not, you have to put something in to make sure that they don't interleave that way. We'll talk about it. It's called synchronization. So I just want you to see, this is the easiest way to see that challenge, that they are concurrent, they are unordered, they could be in any order, and your challenge is to make sure that the answer is still correct when that happens. All right, so I'm going to move on. Someone asked, why is the hello world output ordered on our machines? So the answer is, and this is an important answer, we don't know. It could be the way your operating system is scheduling the threads. It could be the way you're running the program. You don't know. That's the thing about concurrency. Okay. It may run and give you the same answer every single time, and it may be the completely ordered hello then world. It may do it that way. I mean, this is the problem. It may give you that correct, hello world, new line, hello world, new line, hello world. It may do that every single time for 1,000 test runs, and then 1001 it changes it. Now this is scary, because imagine you're writing, an avionics package, and so yeah, the plane flies fine for 1,000 times, and then it crashes. So this is tricky. So here we go. I'm going to dive into the details, and I repeat, if you're still behind because something so far hasn't worked, don't worry too much, because after this section, I'm going to give you an exercise that will take 15 to 30 minutes. And it'll take long enough that we'll be able to have time, to pause and help debug specific problems. So let's go on. Creating threads. Oops, gotta get back in the right screen, sorry. Oh, wait, gee, wow, creating threads, okay. The fundamental execution model in OpenMP, when we're talking about multi-threading, is fork join parallelism. And by the way, this is the fundamental execution model of C11 threads, Java threads, P threads. This is threading, not OpenMP, all of the threading environments. This is what they do. It's called fork join parallelism. So you have an initial thread, and that initial thread's cranking along, doing code, happily marching away, and it hits a point in the program where that thread would sure love to have more threads to help it. So then it forks a team of threads. So that team of threads works together. So that's what we have right here, that first block. It forks a team of threads. Now those threads run concurrently. They're unordered with respect to each other. Now, if I have multiple cores, those concurrent threads will also run in parallel. Parallel means they're actually running at the same time. But they're marching along. And then when they get to the end of that block of code that they were going to do together, they join back together. So fork creates a team of threads, join ends the team of threads. And then that initial thread, that same thread that started this saga, continues. And then you can continue along until you hit another place where you could use more threads. Fork a team of threads. It can be a different number of threads if you want. And they go through and work. So we call these parallel regions. And remember, in OpenMP jargon, when I say region, I mean the directive plus all the code called inside the block with the directive. That's the parallel region. So that your program is a sequence of parallel regions interspersed by sequential parts. And that's the execution model. And it can be nested. If a thread's cruising along inside its team and it goes, oh my God, I could use some help. Fine, fork off more threads, no problem. So this is the fundamental execution model of OpenMP.
Tim, I have a brief question on that nested threads issue.
Yeah.
Does that get tricky? Can you have a situation where you end up with, subthreads, spawning subthreads, and things balloon up and get out of control? Is that something you have to be careful about?
Oh, yes. We call it the oversubscription problem. If I have 20 physical cores, which I think is what you have on your the GPU cluster CPUs, in a single CPU, and they're hyper-threaded, so the operating system thinks you have 40. And so I launch off 40 threads, and if each and every one of them calls a library, this is where this most happens. Imagine I call my handy fancy GraphLaws. That's a project I'm really involved with, deeply involved with. And my GraphLaws library is OpenMP multi-threaded, and so each of them goes and says, hey, okay, cool, default number of threads is 40. All right, now we got 40 times 40 threads. And eventually you get what's called the oversubscription problem, is all the operating system's doing is spending time swapping threads around. Nothing useful happens, you just swamped the system with these hundreds and hundreds and hundreds of threads. So yes, that is a problem. Most people don't use nested parallelism for exactly that reason. But if you're doing an algorithm where you want to use nested parallelism, then you control that. Okay, everyone, the default number of threads is not 40, the default number of threads is 4. There are ways you can explicitly manage that. But yeah, if you just willy-nilly go nesting threads, it can get ugly. I urge you to try it at some point today. Remember, it's important. Play, dink around. You're not going to break something permanently if you bring your system to a halt. All right, so let me talk about in excruciating detail what just happened when we create threads. So a parallel construct is how you create threads. So if I wanted to create a 4-thread parallel region, I would go the following. I have an array, a double precision array A of length 1000. I declare it prior to the parallel region. I call an OpenMP library OMP set num threads 4. So this is me saying to the system, hey, the next parallel region, use 4 threads, please. And make this the default number of threads, 4. So anytime there's a parallel region, until I say otherwise, I'm asking for 4 threads. So then I have the pragma OMP parallel. And then inside, I have the block of code, and every thread will execute that code. Every thread will declare an integer ID. Every thread will put into that integer ID the OMP get thread num return value. And then they'll call a function poo that the users provided, and we'll run. And then I'll have it for each of the threads. So I've introduced 2 runtime functions. This runtime function, OMP set num threads, sets the default number of threads. This is the default number of threads to request. Then I've talked about another runtime function, get thread num, and it's a runtime function that returns a thread ID. And the thread ID is also called a rank. If you hear people talk about ranks, what they're talking about is a number that defines the ID of an execution agent. And you don't need to see my Outlook notices. That ranges from 0 to the number of threads -1. So in this case, if I got 4 threads, I would have 1 thread with the value of 0 for its ID, 1 thread 1, 1 with 2, 1 with 3. Now this concept is so important that I want to walk through it very carefully. So, I reproduce the code in that yellow block so you can see the exact code, and each thread's going to execute the code in that parallel region. So I declare the array A1000. And to a first order of approximation, we'll get down to all the gory details, but to the first order of approximation, if I declare a variable prior to the OpenMP pragma parallel, the pragma OMP parallel, it's shared. All right. So all of the threads will be able to see A. If I declare a variable inside the parallel region, it's private to the thread. So each thread has its own value of ID. So here's the execution. Initial thread declares A, initial threads requests 4 threads. Let's assume I got the 4 threads, so then I fork them off. So then each thread gets its ID, and now I have 1 thread calling the function poo with 0A, another thread 1A, another thread 2A, another thread 3A. Then when I get to the end, all the threads wait at that end. We call that a barrier. And when all of the threads finish their work with those functions, then the initial thread goes on. Now the variable ID that I declared inside, when I go past the end of that closing bracket, it goes away. All right, so if after closing that bracket, I go print all done. If I then go print ID, the compiler is going to say, what's ID? There is no ID. Okay. OpenMP, the variables are tightly scoped. And if I declare the variable between those curly brackets, that's its scope. When I go out of scope, that variable goes away. Okay, now.
Is there anything such as a global variable that you can have go through the whole thing?
Yes, we will talk about that. But it's a matter of C programming style that you avoid global variables at all costs, at almost all costs. But yeah, we'll talk about what if I have a file scope variable. So you can create global variables, and we will get into that, definitely. But to a first order of approximation, and as you're going to see, we come up in this next exercise. With what I've just shown you right now, you can do a huge amount of parallel programming. Just create threads, know how many threads there are, and which I haven't shown you yet, but I will, and know who you are. Okay, any other questions? Not getting any. Okay. You know, it's hard. It's really hard doing this tutorial remotely because I do a lot with your body language. You know, look around the room and look at people in the eye and see who's looking confused or lost. So you really have to work with me here and, you know, and communicate through these various communication channels we have.
Tim,
Otherwise, I have no idea how to paste things. Yes.
yeah, I can see a hand raised by Francis Albert. If you're okay, I can go ahead and unmute him.
Oh, sure,
for a
sure.
question. Okay, well, I think Albert, Francis, you
Yeah, I
can.
think
Okay,
can
yeah,
unmute
go ahead.
now. Okay, so I have a doubt, like there's another task int id OMP get thread. So this task will also be assigned among the 4 threads, or how this will happen?
I'm sorry, I didn't understand.
So we have 2 tasks inside the brackets. So the first line is getting the ID of the thread.
Yes.
And then there's a second task, who ID comma a. So we have 2 tasks.
All right. So let me clarify this. So thank you. By the way, that's a great question in that this is going to help us get something really nailed down here. Okay. There is one task. The task has 2 statements, int ID and calling the function poo. There is one task. There are not 2 tasks. So with the word task, we're going to use very specifically. A task is a sequence of statements and a data environment. So there's one task and it's going to go to one thread. We decompose tasks across threads. The thing is, I've created multiple threads with that parallel region. And each thread has its own task. Int ID equals OMP get non-thread and call poo. In other words, we are not splitting up statements across threads. No. What we are doing is each thread is independently, redundantly running the statements inside those brackets. So we're not splitting up. We are not sharing the work between those brackets. Each thread is redundantly executing the statements. Int ID equals OMP get thread num, and then call the function poo, passing in the parameter ID and A. So what I'm doing though is I have 4 threads executing those statements. So what I've accomplished here is now I have the function poo is running in parallel on 4 different, well, is running concurrently with 4 different threads. And if I have at least that many cores, it's running in parallel on that many cores. Does that make sense?
Yes, yeah, now it's clear for me, yeah.
Good, all right, good. That's a very important one to have down. All right, so I want to pause for a moment because I've been very careful with my words, you've noticed. When I talk about that OMP set num threads, what it does is requests a number of threads. The system can silently give you fewer threads than you ask for. Now, when you first internalize that fact, you may go, oh, so you guys are really obnoxious assholes who want to make our life difficult. If I said I want 1,000 threads, give me 1,000 threads. Well, the problem is, in some cases, on some systems, you ask for 1,000 threads and you got chaos. So the system has the right to say, no. That many threads makes no sense. I mean, imagine, you know, you're a system administrator of a shared resource with, you know, 1,000 cores. Yes, we do build, there are systems with that many cores that are shared among many users. And you may decide that, you know what, no one gets more than 32 threads. So you have to have the ability for the people managing the system to set resource limits. So this is why we built into OpenMP the idea that you can't assume you get the number of threads that you asked for. And there is no way to find that limit. You know, you don't know. You ask for you ask for how many threads you think you want, and you get what you're going to get. Okay, so now we enter the Pragma OMP parallel. We get in there. You ask for the ID. It'll never give you more than you request. Yeah, you will never get more. You could get less. And you know, if your numbers are small, I mean, think about it. It's pretty reasonable. It's pretty logical, actually. You know, if you're asking for a number that's similar to the number of cores, which if you want good parallel performance, you should be. It's rare that there's a reason for you to want more threads than cores. So if you only have, you know, 4 cores on your system, then why ask for more than 4 cores? Or, you know, if you have 20 hyper-threaded cores, you know, you may want 40 or you may want 20, but, you know, you're not going to want 100. So usually these limits work. You're getting into some pretty rarefied concurrent algorithms when you start asking for a lot more threads than there are physical resources to run them. But here's how you do things: is you enter your parallel region. So you always going to get, not always, you're going to ask for your ID. Int ID equals OMP get thread num. Then there's this new runtime function. How many threads did you actually give me? OMP get num threads. That will return an integer which says, how many threads did I actually get? Now, once you get a number of threads, that's the size of your team of threads, they're not going to pull threads away from you. So, you know, if I asked for 4 threads and the system only gave me 2, then n threads would now equal 2. But it's not going to halfway through say, no, I'm sorry, I fibbed, you're only going to get 1 thread. Nope, not going to do that. So once it tells you this is how many threads you got, this is the size of your team, that stays fixed. Okay, so just to review, because you're going to start using these. This is the runtime function to request a number of threads. This is the runtime function to find out how many you actually got. All right, so now what we're going to do for a long time here is we're going to play with what those of us in the parallel computing education business call the Hello World program of parallel programming. If you've had a course in parallel programming, you've probably played with this code, because it's the simplest case we can think of where you're actually doing things in parallel, and if you do everything right, in most cases, it will run faster. So that's what this is all about. And I love dealing with physicists because you all are comfortable with integrals, and you're not confused at all why the integral 4 over 1 plus x squared integrated from 0 to 1 is equal to pi. And you've seen this approximation before, that I want the area under the curve and I can fill it up with rectangles. And that summation notation at the bottom is what I would use to do that. And this is what the C program looks like. And in your exercises, oh gosh, the tag at the bottom of the line is wrong. You know, but in your folder, exercises / OpenMP, you have a file called pi.c, and it has this code. You do not have to type in this code. I give you the pi program. And it should be pretty straightforward. I set the number of steps. I set a step size. Why I did those as file scope variables, I have no idea. It doesn't matter. And then I declare my variables, because in C, old C style, we do that, but you can follow more modern C styles if you want. I declare my step size, then I run over this loop for I equals 0, less than num steps, increment I. Compute my value at the middle of the interval, and then accumulate the sum to get accumulate the integration. Then I'm all done. I multiply by step and I have something that looks like pi. All right. So one last concept before I turn you loose on our exercise. And here I have the correct location of the pi program. It's just the previous slide. I will fix that once you're doing the exercises. So it's in the parprog course exercises OpenMP directory pi.c. And I will answer the question that came up on Discord in a moment. So you want to time things. You want to know how long things took. So we've created a routine called OMP get W time. It returns a double. And this is a common way we do timers. We actually, this name was chosen to align with MPI. W time means wall time, elapsed time. It's the time you'd see if you looked at a clock. It's not CPU time, which is the time accounted to a particular thread by an OS when it's running. What you care about as a human being is, what's the wall time? If I time it with a stopwatch, it should agree with this wall time. And we do the obvious. You ask, what time is it? And then you do what you're going to do. And then you say, okay, how much time has elapsed? So in this program, by these two calls to OMP get W time, I know the elapsed time of the code inside. All right. Now we come to the exercise, and I promise I will get to your question. So what I want you to do, and this will take, it can be as, all of you can be done maybe in 15 minutes, maybe in 30 minutes. We'll see. I want you to parallelize the Pi program using only what we've covered. Those of you who know some OpenMP, do not cheat. You are doing this with Pragma OMP parallel, and you can call these 4 runtime functions to get the number of threads, to get your rank, to get the time in seconds since a fixed point in the past, and to request a number of threads. That's it. Parallelize the Pi program. And as I said, this will take a while. You're going to have to do some serious parallel algorithm thinking to do this. Go. No, wait. Go. Not quite yet. I said I'd answer the question. Can I use cores on more than one node using OpenMP? Okay, I'm going to answer that question. In the world of parallel hardware, the word node means a stop on a network. So when I'm going across stops on a network in distributed computing or distributed memory computing, I'm using parallel programming across nodes. So if you're logged in onto the GPU cluster where we're just using the CPUs, not the GPUs right now, you know, if you go from one node you can SSH into to another node you can SSH into, that would be, you know, that'd be going between nodes. Okay. OpenMP does not go between nodes. OpenMP is for programming a node. Now, the word node can be very complicated. You know, you look at, for example, NVIDIA sells their DGX2, which has one node. What is one node? One node is a pair of beefy Xeon processors with, gosh, is it 8 GPUs? Some number. So a node can be really, really intense in terms of what the hardware resources are. But the key is that when I'm going around to the processors that are on a single node, I'm not going over a network layer. I'm not going through a network stack. I'm going through something much tighter, much tightly integrated. So OpenMP is for programming on a node, not between nodes. All right, that answers the question. Go for it on the exercise. I'm going to go get a cup of coffee, but I will be back and I'll be monitoring the questions. I want the Discord discussion to get noisy. So if you get frustrated, that's good. If you're spinning your wheels, that's bad. If you find yourself spinning your wheels, just going, I don't know what to do, ask a question. We need to make this interactive. So go, have fun. We may have to close this door too, though.
Oh, I do that when I go out.
Well, how's it all going? Has anyone finished this yet? This exercise yet? You know, it all depends on how much background you bring to this course. So I'm going to give some hints because some of you don't need them, in which case ignore what I'm saying now and just keep going. But you know, there's over 50 of you, there's about 50 of you out there. So some of you in that 50 need some hints. So if you think about it, there are two challenges to this problem. There are two things that you have to address in a correct parallel algorithm. One, you have to figure out how to divide loop iterations between the threads. All you have to work with is the thread ID or the thread rank and the number of threads. So I know I have this many iterations, I have this many threads, I have to give a different block of iterations or different set of iterations to each thread. The other problem is you're all summing into a single value. You have the global value sum. And all the threads are writing to that same sum. How are you going to handle that? So I want each thread to create its own partial sum, but I have to be able to then, when they're done, combine those partial sums to create a single global sum. That's challenge number 2. So these are the two things you're going to need to deal with. So go ahead and think about that. And then I'm going to switch back to Discord and take a look at people's questions and be ready to answer questions there.
It looks like Milton is having some trouble with the compiling. Maybe you can help him out a little bit. Tim.
Oh my goodness. Am I supposed to be able to read that little itty bitty text?
If you click on the image, it'll blow up into a larger size that you should be able to read.
Whoa! How do I get back? Escape?
Yes, you can just escape out of it.
Okay. Well, why are you having poo? So you're supposed to be working with the Pi OpenMP, so the Pi program I gave you. And you're confusing me because you're getting an error message where it's complaining about a function poo, and there wasn't a function poo in there. So here's the directory. You know, if you got my code, PAR programming course exercises, there's OpenMP. Inside here is the function pi. This is your starting point. And I'm an old-fashioned programmer, and I put lots of comments to describe everything I do because I'm a good programmer. But there's your starting point. And so the first thing to do is make sure that you can just compile that. So, all right, oops, man. Okay, so on my system, I think I now have it set so I get the right GCC. Well, we'll see. I have to use GCC 9 explicitly. All right, so I do that. And I had to put the -f OpenMP because I have those timing calls in there. So then when I run it, out. So, first thing is make sure you can just run it. So in C, you have to declare a variable before you use it. So vi, if I'm going to call the ID in the middle of a parallel region, this will most decidedly be an incorrect program because there's a lot I'm not doing here, but I can go through and I have to declare, I want an integer ID and its value will be the return that should compile and run. So, the beauty of it is we do these things step by step. And I should get a completely garbage answer because I didn't do any. Well, actually, I don't know. Reproducing it time and time again, I don't know what answer I'll get. Yeah, that's what I thought. So the error, in the code you sent around here on Discord, I'm not sure what you had in your PyOpenMP, but remember, you have to declare. If you're a Python programmer, you get kind of used to just, you want a variable, just use it. In C, you want a variable, you have to declare it first so that you know the type. Which, believe it or not, that's a good thing. And if you're getting an undefined reference to OMP get W time, remember, how did that happen? Remember, at the top, you have to have this count include omp.h. So that's what happens. And then you have to put -f OpenMP on the compiler line. So in other words, you have to tell the compiler, hey, I'm going to throw some OpenMP at you, okay? And it will, that -f OpenMP causes the compiler to look for those pragma, and it causes the linker to link in the libraries needed by OpenMP. Okay, is anyone done in getting Pi? If so, just type in a quick message bragging on Discord. Bragging's okay, man. I'm awesome and done. I'm really great and I'm done. Oh, okay, no, I'm not. I don't mean to put anyone down who's not done. Still not getting the right answer. How do you access each sum from the different threads? That's one of the crux problems. I want you to think hard how you would do that. Okay, so Milton, the poo_id function was just a garbage function I put in there to say I'm calling some function. I'm having every thread. If we go back to that slide, it's quite a ways back. Oh, no, it's not. We can go right here. I just needed some work to do. The purpose of the function poo is that I just needed some work to put in this code. It just, and the point I'm making, and this is the concept I need you to internalize, is each thread was independently calling the function poo. It's a user written function. Some user wrote that function. Okay. It's a PowerPoint thing. I have to have my code fit on a single slide of PowerPoint. And so rather than type lots and lots of code on the slide for the work each thread was going to do, I said, there's a user defined function poo that each person's calling. All right. It's not a piece of OpenMP syntax. I just needed a stupid function name for the user defined function. So I'm sorry that was a point of confusion for you. So ignore it. Does that make sense? I'm sorry that became a point of confusion. Gosh, I look forward to when we can do these things face to face. Because this is just these sorts of things that we communicate as humans so much through nonverbal cues, and we lose that. Even with video, we lose it. But yes, that the question earlier, I'm going to tell you that a tough part of this is how do you deal with the partial sums? Okay, so we're far enough into this that I'm going to start saying a little bit more. So, and I have weird white space use here. Sorry. It doesn't matter. In C and Fortran, white space is strictly a matter of aesthetics. But for some reason, it really matters to me. All right. So here's the problem. First thing to note, I'll get to that later. Sum is a shared variable. I declared it up top. So sum is a shared variable. And all the threads are making modifications to that same shared variable. And they're making modifications to that same shared variable and stomping all over each other, right? Think about it. Thread 0 is about to accumulate its result into sum. And while it's halfway through that, thread 1 is going to go through and write its value into sum. So then thread 0 will write its value and overwrite what thread 0 just wrote. So it's a total chaos. And you can see that when, okay, so I compiled my program earlier. Run it. Hope this works. Run it. Run it. Look at the values of pi I'm getting. Each time I run it, the value of pi is a little bit different. Do you see that? So we call that a race condition. When the output of your program is different, depending on how the operating system schedules the threads, you have a race condition. In almost all cases, a race condition occurs when you have a data race. And that's what we have here with sum. Come on down and look at this code. All right. Everyone's just writing into sum. Remember, I told you the statements are interleaved. So, well, one thread is reading it. So if you think about that statement, sum equals sum plus 4.0 over 1.0 x, right? Okay, think about that statement. You read sum because you need to have the latest value. You do the operation 4 over 1 plus x squared. You add it to sum, and then you write it back to sum. So one thread reads it. After it reads it, another thread writes back its value. Then the other thread writes back its value. Halfway through it, writing back its value, another thread tries to read it. It's chaos. That's called a data race. This statement right here is called a data race. And they are so ugly, they are so messed up that language definition in C and C++, it says any program with a data race is undefined. The compiler is not required to do anything. It's undefined. So what we need to do is give each thread its own copy of sum to program into. All right, x, comma, sum. All right, cool. Now each thread has its own copy of sum to sum into. Whoops. Yeah, it's really hard typing live. Now what do I get? Okay, every thread. Oh, why is it 0? Why is it 0? Well, at least I'm getting exactly the same answer each time. So no data race. What we have to do, remember, at the end, there's a curly bracket, there's a curly bracket. At the end of the curly bracket, sum doesn't exist anymore. It goes out of scope. So when I get to this statement, pi equals step times sum, there is no sum. It's a mess. So what am I going to do? Well, here's what I'm going to do. I'm going to go up here and I'm going to declare an array of num threads. I'm going to define num up here. Let's say pound define num 4. Okay, let's say 4. And go over here and I'm going to ask OMP set num threads. Okay, so now I have an array, it's shared. And so now inside of here, I'm going to index this array by ID. Oh, but I didn't declare it 0, right? You gotta initialize your accumulator. Okay, so you see what I did here. I've now created an array. So now when I get down here, I can do for I equals 0, I less than num, I plus plus, pi equals step, pi, pi plus equals step times, oh, let's say do it this way. All right. Then I have to do this. So you see what I did by promoting some.
Specifically with regard to the index used for the sum array, shouldn't that be an uppercase ID instead of
Yes.
lowercase ID?
Yes.
Okay.
Case matters in C. Thank you. And I assure you, the compiler would have caught that for me right away. Oh, but now I'm masking some, so I got to get rid of the declaration of it there. Okay, so now I go through, and I'm sure there's a bug because I've entered a lot of code. Oh, okay. Oh. Where did I have a sum? Oh, of course. Huh. Well, I'm still not getting the right answer. Can anyone see why? What did I do here? I'm having each thread go through the full loop. I did nothing to split up. Yeah, I've not split up my value.
Your answer looked a lot like 4 pi.
What's this? Yeah, it does look like 4 pi. Oh, it should. Watch this trick. This is the easy way to split up a loop. So now I have each loop start at its ID. And then for the increment, I equals I plus num. Whoa. See? So now one thread starts at 0, one thread starts at 1, another thread starts at 2, up to 3. And I'm incrementing by the number of threads. So it's like dealing out a deck of cards, right? So thread number 0 will do iteration 0, iteration 4, iteration 8, iteration 12. Thread 1 will do iteration 1, iteration 5, iteration 9. So I interleave the iterations. It's called a cyclic distribution. In terms of laziness, easily splitting up a loop, that's all there is to it. It's not the only way, but that's the lazy way.
So Tim, you made a very good analogy there of dealing cards, one card to each person and around. Is there any reason to do it sort of sequentially, where you give the first num steps over num
Yes.
to the first thread, and then another block to each thread from there?
Right. And here's what he's talking about. Okay, so as we come on down here, the other approach is, and I always make mistakes when I do this because you have to, now I'm doing more logic. Int start block and block. I'm making another big bug. Someone should note it soon, I hope. So I could go start block equals ID times num steps over num. And I have to do times there.
What about the case of the ID?
Oh, right, case of ID. All right, and then the other one, end block equals start block plus num steps over num. Here's a cute trick. If ID equals num, end block equals num steps. You see why I did that? This is a cool little trick. What if num steps doesn't evenly divide by the number of threads? All right. If I do that, if num steps over num, if it doesn't evenly divide, if I have a remainder, I'm sorry, if it doesn't evenly divide, then this logic here, the end block, will leave some dangling iterations of the loop that don't get handled. So what I'm saying here is, if I'm the last sorry, if I'm the last thread, make end block equal num steps. Now I know that I'm running all of them. So now I go start block, and I go end block, and I just increment I.
And you're guaranteed that start block and end block will both be integers because you're multiplying and dividing integers, and that won't give you a floating point result. Is that correct?
That is correct, because I'm doing division by integer. I'm doing integer division. And I'm guaranteed that that's returning integer. So now this kind of logic here is so easy to get wrong in small ways. That's why I'm very nervous doing this live. But that's another way of doing it. Now, that was a lot more code. That was a lot harder. What are the advantages of doing it this way? And this is, you know, if we were together. All right, before I go there, Cameron, you are awesome. Because there is a bug I've purposely been making. Remember what I told you, you request a number of threads. You may not get that number of threads, right? How can I, why do I assume that I know the number of threads? I don't. So I have to put inside, isn't parallel programming fun? I have to put inside int n thread equals OMP get num threads. You have to ask how many threads you got. Now, it turns out that for that if you're like in my case here, I'm running on my laptop and I'm running, you know, num is the number of cores my system thinks I have in my laptop. So I'm gonna get that number. Okay, so it turns out that, yeah, it's okay, but it's possible that that program would fail because I could get a different number of threads. Does everyone see that? Yeah, full of off by one errors. Boy, you are right. You are definitely right. All right, code's starting to look ugly, isn't it? Just, you know, like, oh, our simple, elegant, beautiful code. But hopefully you can see the logic. Now, it doesn't matter for this code because I'm just doing local operations. You know, give me X, accumulate the X values into my sum array. You know, there's no issue of cache reuse. But imagine I was doing, you know, multiply. Imagine if inside my loop, I was, you know, doing a matrix multiplication, or I had, you know, another loop inside here and I was walking over an array. So this block structure can make better use of your caches as opposed to the cyclic distribution. And you won't see it in this program, but there are some programs, and we may even run into them before the day is over, where you get a big performance boost by doing it this way, because you want the compiler to vectorize the loop. And we'll be able to talk about that later. I don't want to go too far off. Now, why does OMP get num threads need to be inside the parallel region? Well, let me ask the question here. Before I run it, what's that answer going to be? How many threads are there if I ask before the parallel region? One, right? One. OMP num threads tells you how many threads do you have right now. Okay, it tells you how many threads you have right now. Well, before I've created the threads, there's only one thread. All right, so I went very fast in that logic I did right here. So let me go a little bit slower. And the logic I'm talking about is this logic here. All right. Now I have a number of steps. I want to divide those steps between the threads. So I need to know how many threads there are. I find out how many threads there are, n threads. So if I had 100 steps and 4 threads, I want to give 1/4 of the steps to each thread. Num steps divided by n threads gives me what's the number of steps I want to give each thread. Okay, so the first thread I want to do, okay, so if num steps equals 100 and num n threads equals 4, then 100 divided by 4 is 25. If I give 25 loop iterations to each thread, I will have all of the iterations covered. So thread 0 is going to get iteration 0 to 25. Okay, and you see that's what I get right here. And by the way, this is how I reason it, as I think of numbers I can do in my head, and I make sure that my logic gets it right. So I want to start at ID equals 0 for the first thread, so I want it to start at block 0, and I want it to finish at where it started plus 25. That's correct. I want thread number, I want thread number, I want it to go from 0, not to 25. I want it to go to 0 to 24. Ah, come on. Off by 1 errors. Gee, yeah. I want first thread to go 0 to 24. I want the second thread to go 25 to 49. Okay, and then I check my arithmetic. Okay, that works. And so what if instead of num steps equals to 100, num steps is equal to 105, let's say, okay? So now the number of threads doesn't evenly divide the number of steps. So that means by this logic in start block and end block, I don't do the last 5 iterations. So that's why I had that trick. If I'm the last thread and at num steps, then I know that I always cover all the iterations. All right. How do I know that set the size of the sum array before you know the number of threads? Excellent question. I cheated and took the easy way out. Notice what I did is up here, I set the maximum number of threads I would ask for. So I built into my code, the maximum number of threads I'm ever going to ask for is pound define num equals 4. Now that's a pain if I'm writing a piece of code and that piece of code is going to run on a variety of systems. Because right now I have to recompile. You know, if I moved from my laptop where num4 makes sense to the GPU cluster you guys are using where num equals 40 makes sense, I wouldn't want to recompile it. All right. So there is a way, and I'm hesitant to talk about it now, but I'm going to do it just very, very briefly. There's a function OMP get max, I may even be misspelling it, max threads. All right. You can call that to get max. And then I would do a sum, you know, I would declare sum as double pointer to double sum. Then I would malloc equals double pointer. You see why I don't do that here? Malloc max times size of double. So I can dynamically allocate it. And in a production code, if I was doing this type of algorithm, that's what I would do. But for teaching all this for the first time, that's just like, oh my God, especially if people aren't comfortable with all the C-isms. Okay, so ignore all that. Now, So that max num threads, it basically says what's the default number of threads. If I ask for just a number of threads off the cuff, what is that default set to? That's what max does. So that's how I get the number of threads. And that's how I can allocate just that right number. But no, there is no way to find out. If the system's going to give you fewer threads than you're going to ask for, there is no way to know that in advance. And that actually sounds bad, but it's done for a good reason. There's one other bug in this program, then we need to take a break because I've been talking to you. I normally like to take a break every 90 minutes. And you guys are amazing to be going at it still right now. All right. Here's a problem. I said I less than num. If I got different number than num, I'm now doing a sum into array elements that were never initialized and never set. You see that? You know, I declare array sum of size num, but I never declare it. You know what? Let me go back to the slides because I think it's time to do that now. And then we'll come to a break. So when I get down to that sum at the bottom, so I go I equals 0, I less than n threads, I'm going to increment I, and then I do this sum into pi down here at the bottom. I have to make sure that the number of threads I'm going over is the actual number I got. So I can't correctly use num threads in that sum. What's the solution? What I have to do is I have to declare a shared variable. In this case, it's nTHRDS is a shared variable. I'm sorry. I'm sorry. I have to have a shared variable, n threads. Each thread locally gets its own copy n threads. That's the same as the code I had before. But I arbitrarily pick one thread. So if ID equals 0, I just picked one of the threads. Doesn't matter. It didn't have to be 0. And in that thread, I set the shared variable n threads to n threads. So one thread and one thread only copied the value of the number of threads from inside the loop into the shared variable n threads. And so now I know, remember, at the end of this closing bracket, all those variables I declared inside parallel construct go away. X goes away, I goes away, ID goes away. You know, they all go away. They don't exist anymore when you go out of scope. So if I want to know after the parallel loop what the number of threads was, I have to copy it into that shared variable. So now when I get to this loop right here, I correctly go over the actual number of threads I got. All right. So any remaining questions? And we're going to take a 15-minute break here in a moment.
So Tim, a quick question for you on that, that when you say the issue there, why you have to choose one and only one thread to do this, that's not necessarily because you'll have the same value of nTHRDS in each thread. It's just so that you don't have a race condition where all 4 threads, let's say, are trying to write to the same global variable at the same time and it crashes the program. Am I understanding that right?
So you're absolutely right. So let me be clear. And this is an interesting little anecdote. For the longest time, when I wrote this code, I would not have one thread do it because they're all writing the same value. N threads equals nTHRDS. They're all going to write the same value. I don't care then, so why worry about it? And the problem is that because I work at Intel, and I've worked at Intel for many, many years, on an Intel system, that's guaranteed to work. Intel, the memory model, we'll say more about memory models later. The Intel memory model is really forgiving. It protects you from screwing up. So it says that if you're doing a basic write, if you're doing a load or a store of the built-in variable type, we guarantee it will happen atomically. So they will not stomp on each other. They will all, one thread will write the value 4, the next thread will write the value 4, and each one of those individual stores won't overlap and give you chaos. So the Intel memory model, the x86 memory model, protects you when that code's correct. But you move to ARM, you move to the IBM Power, and it can blow up in your face. You don't know what value you'll get because it's a data race. So even writing the same value to the same memory location by multiple threads, depending on how the circuits in the chip manage that write, they could stomp all over and you can get chaos. It's a data race. So even writing the same value could be a data race. So I had to do the if ID equals 0 to make sure that I didn't have a data race. And this is why for code I really care about now, what I do is I have good friends at the University of Bristol. They have a system called Isambard, and it's wonderful, and they let me use it for my testing. Because in there they have an IBM Power, they have an ARM chip, they have an Intel chip, they have an NVIDIA GPU, an AMD GPU, an Intel GPU. So you have to do cross-architecture validation if you really care about the code, because without that if ID equals 0, it's fine for x86, it's not fine for anything else. And it is technically a race condition if I don't include it. And I've now gone into way too much detail and you folks need a break. So let's take a 15-minute break. We'll start up.